So just remember what we talked about in terms of ionization and our ions in the context of radius and ionization energy. Okay, so that's atomic radius and ionization energy. The bigger the radius, the easier it is to ionize. So the larger radius equals lower. I'm just going to do ionization energy as IE. Larger radius equals low ionization energy. So they are inversely proportional to each other. All right, even though the numbers here don't reflect that, but I should have chosen maybe a different set of numbers for the first one, but here we are. So just remember this trend. It's very important. Okay, on to the last topic, I believe. Yep, on to the last topic. I think we're at like 20-some minutes now, so if you're still here, proud of you. You only have to hang on for a little bit longer while we do this, and then hopefully you'll be ready for the exam. So let's get started on this one. So CCl4. These are Lewis dot structures, by the way, and geometry and polarity. So CCl4 is carbon tetrachloride. The first thing that you should do is think about what the center atom is going to be. So in this case, we have 1 carbon and 4 chlorines. So it makes sense that the carbon would be the center atom, right? So we're going to have carbon sort of arranged around the chlorines like that. Okay, kind of like that. Once you have that idea in mind, then we can actually start putting the thing together. So carbon has 4 valence electrons because it's in 4a, the group 4a. So look at your periodic table for that. And chlorine is in 7a, so that's going to have 7. Okay. So 4 plus 7 times 4 is going to be 28 plus 4, so that's 32 electrons. So that's how many electrons we need to have in the end. And you should calculate this because this will also tell you about double bonds and other things too. So what do we need to do? We need to put our carbon in the middle, add our chlorines with single bonds. And I do single bonds first, and then I'll form the double bonds. So I like to do the single bonds because this way it sort of sets the framework, and then if we need the double bonds, they can come later. But this single bond, remember, is called a sigma bond. And that sigma bond is that first single bond that you're forming. So if we're adding up or we're putting in all of our 32 electrons, carbon has 1, 2, 3, 4 initially, right? So these bonds came from pairs. 1, 2, 3, 4, that's carbon's 4 valence electrons. Now chlorine needs to have 7, and it currently just has 1, right? That one that it's sharing. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2. Okay, and so now we have 1, 2, 3, 4, 5, 6, 7. That 7th electron is still there, right? It's being shared though. So this is what the Lewis dot structure would look like for carbon. And if we add up all of our electrons, we have 7 for each of the chlorines. And then we have 1, 2, 3, 4. You could also count this as 6, 6, 6, and 6, and then 2, 2, 2, and 2, and that would still add up to 32. But the Lewis dot structure is actually this. It's just... And if you're lazy, you can use these bars as lone pairs as well, which is what I normally do. But I'll try to avoid that because it's kind of confusing when I draw it that way. What geometry is it going to have? This will be tetrahedral, so you should consult your geometries page because this has 1 center atom with 4 atoms around it and no lone pairs. So it will be a tetrahedron. The bonds are not polar. This is not a polar bond. Well, it's very, very slightly polar, maybe. Not polar enough. But these are all identical atoms, so they're all pulling on that carbon with the same strength, which means that the electrons will be distributed evenly. And that's what polarity is where the electrons are distributed. So the electrons being distributed everywhere means that this will be non-polar. Okay? All right. So that's kind of a general idea of how you're supposed to approach it, and I'll go a little bit faster through the next few of them and just try to follow along. So nitrogen. Nitrogen is in group 5, so this is going to be 5, and then iodine's in 7. So we're going to end up with 7 times 3. That is 21. 21. And 21 plus 5 is 26, so we should have 26 electrons in this guy. Put nitrogen in the center because, you know, we have 3 iodines. And I'm just going to draw it this way. No, we're not going to do that. We're just going to do a bond. I'm just going to draw it this way for a reason that you'll see why in a minute. So if we do all of our bonds this way, we have 2, 4, 6 electrons, but we still need 20. Okay? So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Now we have 6, 6, and 6. That's 18. 1, 2. That's 20. We now have our Lewis dot structure. So we have 2, 4, 6, and then we have 8. And then plus all the iodines should equal 26. Everything has an octet. So everything either has 8 electrons or is sharing electrons that adds up to having 8 electrons. So this iodine here has an electron, and then it's also sharing an electron, so it has that octet. And the same thing with nitrogen. Okay? And so this is going to be the Lewis dot structure. And the reason I drew it this way is because this is actually what the geometry will look like. Is if you want to look at it in 3D space, it looks like this. If you can see my hand. So it's actually a pyramid. It's actually a trigonal pyramid that stands like that. So because it is that trigonal pyramid, and nitrogen is electronegative, and iodine is not very electronegative, it's very far down that column. It's actually the farthest, or I guess astatine, but still. It's quite far down. So this is a very polar compound. This will be polar because the electrons will mostly be shifted towards that nitrogen. And so you're going to end up with a pyramid with a lot of electrons up here, and then not very many electrons. So then you end up with a very strong negative charge, very strong positive charge. Okay? Or partial positive and partial negative, since these are not full charges. Oh, shoot. I wrote polar under geometry. So it's polar, yes, but the geometry, which we should have done first, is trigonal pyramidal. Or just pyramidal, I think. Pyramidal should be fine because it's a pyramid. But trigonal pyramidal is more specific as to what kind of pyramid it is. And so this geometry comes from the fact that we have this one lone pair. So check your geometries again. You have one lone pair up here, and that's going to push all of those iodines down. And that's going to push them into that shape. That's a pyramid. Okay? So that is Ni3. Just going to draw a line right there. Draw a line right there. All right. Let's do CO2. Okay?